Hello and welcome. In this video, we will explore the fundamental rules of differentiation, a core topic in IB mathematics, analysis, and approaches higher level. By the end of this session, you will be able to apply the power rule, constant multiple rule, and sum/difference rule to find derivatives of polynomial and rational functions. You will also learn to interpret the derivative as a gradient function and an instantaneous rate of change. Let's begin with a familiar function. Consider the curve y equals x squared. We know from first principles that its gradient function, or derivative, is dy by dx equals 2x. This function tells us the gradient of the tangent line at any point x on the curve. Now, let's think about a key feature of this curve. At what point is the tangent to the curve horizontal? A horizontal tangent has a gradient of 0, so we need to find the x value where the derivative, 2x, is equal to 0. Setting 2x equal to 0 gives us x equals 0. This corresponds to the vertex of the parabola, which is the point 0, 0. This demonstrates how the derivative function can be used to find important features of a curve. Now, let's investigate how transformations of a function affect its derivative. This will lead us to our first differentiation rules. First, consider the transformation from y equals x squared to y equals x squared plus 3. This is a vertical translation. The entire graph of y equals x squared is shifted upwards by 3 units. For any given x value, the y value is simply 3 greater than before. Has the gradient of the tangent changed? Visually, the slope of the tangent line at any x value appears to be the same for both curves. The derivative of y equals x squared is 2x. What do you think the derivative of y equals x squared plus 3 is? It's also 2x. This suggests that adding a constant to a function does not change its derivative. This leads to our first rule. The derivative of a constant is 0. If f of x equals c, where c is any constant, then its derivative, f prime of x, is 0. This makes sense, as the graph of a constant function is a horizontal line which has a gradient of 0 everywhere. Next, let's look at the transformation from y equals x squared to y equals 2x squared. This is a vertical stretch by a factor of 2. The graph becomes narrower. For any x value, the y value is now twice as large. How does this affect the gradient? The derivative of y equals x squared is 2x. The derivative of y equals 2x squared is 4x. Notice that the new derivative, 4x, is exactly twice the original derivative, 2x. This suggests that multiplying a function by a constant also multiplies its derivative by that same constant. This is our second rule, the constant multiple rule. If f of x equals c times u of x, where c is a constant and u of x is a differentiable function, then its derivative is c times the derivative of u of x. In other words, you can pull the constant out of the differentiation process. Now we're ready to state the most important rule for differentiating polynomials, the power rule. The power rule states that if f of x equals x to the power of n, then its derivative, f prime of x, is n times x to the power of n minus 1. You bring the power down as a coefficient and subtract 1 from the power. Let's see this in action with a few examples. If f of x equals x cubed, then n is 3. Applying the rule, we get 3 times x to the power of 3 minus 1, which simplifies to 3x squared. If f of x equals x to the power of 8, then n is 8. The derivative is 8 times x to the power of 8 minus 1, which is 8x to the 7th. The power rule is incredibly versatile. It works not just for positive integers, but for any real number n. This includes negative numbers and fractions. For example, let's differentiate f of x equals 1 over x squared. First, we must rewrite it in the form x to the power of n. Using index laws, 1 over x squared is x to the power of negative 2. Now, n is negative 2. The derivative is negative 2 times x to the power of negative 2 minus 1, which is negative 2 x to the power of negative 3. We can write this back as a fraction, negative 2 over x cubed. Let's try another one with the fractional power. Differentiate f of x equals the square root of x. The square root of x is x to the power of 1/2, so n is 1/2. The derivative is 1/2 times x to the power of 1/2 minus 1, which is 1/2 x to the power of negative 1/2. This can be written as 1 over 2 times the square root of x. Now we can combine the power rule with the constant multiple rule to differentiate more complex terms. Let's differentiate f of x equals 5, x cubed. Here, the constant c is 5, and the function u of x is x cubed. Using the constant multiple rule, the derivative is 5 times the derivative of x cubed. We know the derivative of x cubed is 3x squared, so the final answer is 5 times 3x squared, which is 15x squared. Let's try another. Differentiate f of x equals 7x to the power of 4. The constant is 7. The derivative is 7 times the derivative of x to the power of 4. The derivative of x to the power of 4 is 4x cubed. So we have 7 times 4x cubed, which is 28x cubed. This combination is very powerful. It allows us to differentiate any term of the form c times x to the power of n. The general rule is the derivative of c times x to the power of n is c times n times x to the power of n minus 1. You multiply the existing coefficient by the power and then subtract 1 from the power. Let's apply this to a term with a negative power. Differentiate f of x equals negative 4 over x. First, rewrite it as negative 4 times x to the power of negative 1. Here, c is negative 4 and n is negative 1. The derivative is negative 4 times negative 1 times x to the power of negative 1 minus 1. This gives us positive 4 times x to the power of negative 2, which is 4 over x squared. The final rule we need for polynomials is the sum and difference rule. This rule states that the derivative of a sum or difference of functions is the sum or difference of their derivatives. In other words, you can differentiate each term in a polynomial separately. Let's put all these rules together to differentiate a full polynomial. Consider the function f of x equals 5x cubed plus 6x squared minus 3x plus 2. We can differentiate this term by term. The derivative of 5x cubed is 15x squared. The derivative of 6x squared is 12x. The derivative of negative 3x is negative 3. And the derivative of the constant 2 is 0. Combining these, we get f prime of x equals 15x squared plus 12x minus 3. This process is much faster and more efficient than using first principles. Let's try a more complex example involving fractions and roots. Differentiate f of x equals 3 times the square root of x plus 2 over x. First, rewrite the function using index notation. The square root of x is x to the 1/2, and 2 over x is 2 times x to the negative 1. So, f of x equals 3x to the 1/2 plus 2x to the negative 1. Now, differentiate term by term. The derivative of 3x to the 1/2 is 3 times 1/2 times x to the negative 1/2, which is 3/2 x to the negative 1/2. The derivative of 2x to the negative 1 is 2 times negative 1 times x to the negative 2, which is negative 2x to the negative 2. Finally, rewrite the answer with positive indices and roots. This gives us f prime of x equals 3 over 2 times the square root of x minus 2 over x squared. Sometimes, a function is not immediately in a form that can be differentiated using our rules. In these cases, we must first simplify or expand the expression. Consider the function y equals the quantity x plus 1 times the quantity x minus 2. We cannot differentiate this term by term. We must first expand the product. Expanding the brackets gives us y equals x squared minus x minus 2. Now this is a simple polynomial that we can differentiate. The derivative of x squared is 2x. The derivative of negative x is negative 1. The derivative of negative 2 is 0. So dy by dx equals 2x minus 1. Let's look at another example. Differentiate y equals the quantity 2x minus 1 squared. Again, we must expand first. Squaring the binomial gives us y equals 4x squared minus 4x plus 1. Now we can differentiate. The derivative of 4x squared is 8x. The derivative of negative 4x is negative 4. The derivative of 1 is 0. So dy by dx equals 8x minus 4. Finally, let's differentiate y equals the quantity x squared minus 3, all divided by x. We can split this into two fractions. This gives us y equals x squared over x minus 3 over x, which simplifies to y equals x minus 3x to the negative 1. Now we can differentiate. The derivative of x is 1. The derivative of negative 3x to the negative 1 is negative 3 times negative 1 times x to the negative 2, which is positive 3x to the negative 2. So dy by dx equals 1 plus 3 over x squared. A key application of differentiation is finding the gradient of the tangent to a curve at a specific point. Let's find the gradient of the tangent to the curve y equals x squared minus 4 over x at the point where x equals 2. The first step is always to find the gradient function, dy/g(x). First, rewrite the function as y equals x squared minus 4x to the negative 1. Differentiating term by term, we get dy by d x equals 2x minus 4 times negative 1 times x to the negative 2, which simplifies to 2x plus 4 over x squared. Now that we have the gradient function, we can find the gradient at our specific point. Second step is to substitute the given x value into the derivative. We need to find the gradient when x equals 2. Substituting 2 into our derivative, we get 2 times 2 plus 4 over 2 squared. This is 4 plus 4 over 4, which is 4 plus 1, giving us a final gradient of 5. So the gradient of the tangent to the curve y equals x squared minus 4 over x at the point where x equals 2 is 5. This means that at that specific point, the curve is rising with a slope of 5. The derivative has a very important physical interpretation. It represents the instantaneous rate of change. Let's consider a classic example from physics. The position of a car moving along a straight road is given by the function s equals 2t squared plus 4t, where s is the position in meters and t is the time in seconds. We want to find ds/dt and interpret its meaning. ds/dt is the derivative of position with respect to time. The derivative of 2t squared is 4t, and the derivative of 4t is 4. So ds/dt equals 4t plus 4. What does this represent? The rate of change of position is velocity. Therefore, ds/dt is the instantaneous velocity of the car at any given time, t. It tells us how fast the car is moving and in what direction at that exact moment. Now, let's find the value of ds/dt when t equals 3 seconds and interpret that answer. We substitute t equals 3 into our velocity function. This gives us 4 times 3 plus 4, which is 12 plus 4, or 16. The units are meters per second. So at exactly 3 seconds, the car's instantaneous velocity is 16 meters per second. This means that if the car were to continue moving at that exact speed, it would travel 16 meters in the next second. Let's work through a more advanced problem that combines several concepts. We are given the function f of x equals x squared plus the quantity b plus 1 times x plus 2c. We are also given two conditions, f of 2 equals 4 and f prime of negative 1 equals 2. Our goal is to find the values of the constants b and c. Let's start with the first condition, f of 2 equals 4. This means that when x is 2, the function's value is 4. We substitute x equals 2 into the original function. This gives us 2 squared plus the quantity b plus 1 times 2 plus 2c, all equal to 4. Simplifying this equation, we get 4 plus 2b plus 2 plus 2c equals 4. Combining the constants, we have 2b plus 2c plus 6 equals 4. Subtracting 6 from both sides gives us our first equation. 2b plus 2c equals negative 2. Now for the second condition, f prime of negative 1 equals 2. This involves the derivative, so we must first find f prime of x. Differentiating f of x, we get f prime of x equals 2x plus the quantity b plus 1. The derivative of 2c is 0. Now we substitute x equals negative 1 into the derivative and set it equal to 2. This gives us 2 times negative 1 plus the quantity b plus 1 equals 2. Simplifying this equation, we get negative 2 plus b plus 1 equals 2. This simplifies to b minus 1 equals 2. Adding 1 to both sides, we find that b equals 3. We have found b. Now we can find c by substituting b equals 3 into our first equation. Substituting b equals 3 into 2b plus 2c equals negative 2, we get 2 times 3 plus 2c equals negative 2. This is 6 plus 2c equals negative 2. Subtracting 6 from both sides gives 2c equals negative 8. Dividing by 2, we find that c equals negative 4. So, by using both the function and its derivative, we have successfully found the values of the constants. b equals 3, and c equals negative 4. Let's recap what we've learned today. We've covered the essential rules for differentiating polynomial and rational functions. We started with the power rule, which is the foundation for differentiating terms of the form x to the n. We then added the constant multiple rule and the sum and difference rule, which allow us to differentiate entire polynomials term by term. We also saw how to handle functions that aren't immediately in the right form. Remember to always rewrite functions using index notation for roots and fractions, and to expand any products or quotients before differentiating. Finally, we explored the meaning of the derivative. The derivative function dy/dx gives us the gradient of the tangent to a curve at any point. It also represents the instantaneous rate of change of one variable with respect to another, which has wide applications in physics, economics, and other fields. You are now equipped to tackle a wide range of differentiation problems. The key is practice. Let's move on to some practice questions. Here are 5 practice questions designed to test your understanding at an IBHL level. I recommend you pause the video, attempt them on your own, and then resume to check your solutions. Question 1. Differentiate f of x equals 3x to the power of 4 minus 2 over x squared plus 5 times the cube root of x. Question 2. Find the gradient of the tangent to the curve y equals the quantity x plus 2 times the quantity 3x minus 1 at the point where x equals 1. Question 3. The volume 5 of a sphere is given by v equals 4/3 pi r cubed. Find the rate of change of the volume with respect to the radius, dv/doctor, and interpret its meaning. Question 4. Find the coordinates of the point on the curve y equals x cubed minus 3x squared plus 5 where the tangent is horizontal. Question 5. The function f of x equals ax squared plus b over x has a gradient of 1 at x equals 1 and a gradient of 5 at x equals 2. Find the values of the constants a and b. Let's go through the solutions. Here is the solution for question 1. First, we rewrite the function using index notation. f of x equals 3x to the 4 minus 2x to the negative 2 plus 5x to the 1/3. Now, we differentiate term by term. The derivative of 3x to the 4 is 12x cubed. The derivative of negative 2 x to the negative 2 is positive 4 x to the negative 3. The derivative of 5x to the 1/3 is 5/3 x to the negative 2/3. Finally, we write the answer with positive indices and roots. The final derivative is 12x cubed plus 4 over x cubed plus 5 over 3 times the cube root of x squared. Here is the solution for question 2. First, we must expand the function y equals 3x squared minus x plus 6x minus 2, which simplifies to y equals 3x squared plus 5x minus 2. Next, we find the derivative, dy by dx. The derivative of 3x squared is 6x, and the derivative of 5x is 5. So, dy by dx equals 6x plus 5. Finally, we substitute x equals 1 into the derivative. This gives us 6 times 1 plus 5, which equals 11. The gradient of the tangent at x equals 1 is 11. Here's the solution for question 3. We are given the volume formula v equals 4/3 pi r cubed. We need to find the derivative of v with respect to r, d, v slash drive. The term 4/3 pi is a constant. We differentiate r cubed to get 3r squared. Multiplying by the constant, we get dv slash doctor equals 4/3 pi times 3r squared, which simplifies to 4 pi r squared. Now for the interpretation. dv slash doctor represents the instantaneous rate of change of the sphere's volume with respect to its radius. In other words, it tells us how much the volume is increasing for a small increase in the radius. Notice that the formula for dv slash doctor is the same as the formula for the surface area of a sphere. This is a beautiful connection in calculus. Here is the solution for question 4. A horizontal tangent has a gradient of 0, so our strategy is to find the derivative, set it to 0, and solve for x. First, we find the derivative, dy by dx. The derivative of x cubed is 3x squared. The derivative of negative 3x squared is negative 6x. The derivative of 5 is 0. So dy by dx equals 3x squared minus 6x. Next, we set the derivative equal to 0. 3x squared minus 6x equals 0. We can factor out 3x, giving us 3x times the quantity x minus 2 equals 0. This equation is true if 3x equals 0, which means x equals 0, or if x minus 2 equals 0, which means x equals 2. These are the x-coordinates where the tangent is horizontal. To find the full coordinates of the points, we must substitute these x values back into the original function. When x is 0, y is 5. This gives us the point, 0, 5. When x is 2, y is 1. This gives us the point, 2, 1. These are the 2 points on the curve where the tangent line is horizontal. Here is the solution for question 5, our final problem. We are given the function f of x equals ax squared plus b over x. We have 2 conditions about its gradient. First, we need to find the derivative, f prime of x. Rewrite the function as f of x equals ax squared plus bx to the negative 1. Differentiating, we get f prime of x equals 2ax minus b x to the negative 2, which is 2ax minus b over x squared. Now we use the 2 conditions to form a system of equations. The first condition is f prime of 1 equals 1. Substituting x equals 1 into our derivative, we get 2a minus b equals 1. This is our first equation. The second condition is f prime of 2 equals 5. Substituting x equals 2 into the derivative, we get 2a times 2 minus b over 2 squared equals 5. This simplifies to 4a minus b over 4 equals 5. Multiplying by 4 to clear the fraction, we get 16a minus b equals 20. This is our second equation. We now have a system of 2 linear equations with 2 variables. We can solve this using elimination. Subtracting equation 1 from equation 2, the b, terms cancel out. We get 14a equals 19, so a equals 19 over 14. Now, substitute this value of a back into equation 1. 2 times 19 over 14 minus b equals 1. This simplifies to 19 over 7 minus b equals 1. Solving for b, we find that b equals 12 over 7. So, the constants are a equals 19 over 14 and b equals 12 over 7. This problem demonstrates how differentiation can be used in conjunction with algebra to solve for unknown parameters. That concludes our exploration of the simple rules of differentiation. You have now seen how to apply the power, constant multiple, and sum/difference rules to find derivatives of various functions. We have also practiced interpreting the derivative as a gradient function and an instantaneous rate of change, which are crucial for understanding its applications. Keep practicing these rules, as they form the foundation for all of calculus. Thank you for watching, and good luck with your studies.